So next topic deals with the voltage regulation. So in simple terms, or if we formulate this voltage regulation, it can be defined as the ratio of E2 minus V2 upon E2. Okay. So what is this E2 and V2? This is nothing but the secondary side EMF. E2 is the secondary side EMF. Okay. When no load is connected. Okay. And V2 is the secondary side voltage or the terminal voltage across load when full load is connected at a specified power factor. So it is usually expressed as the percentage of the rated terminal voltage or secondary voltage, and it is defined as the change in the magnitude of the terminal voltage when full load of specified power factor is supplied at the rated voltage is thrown off to no load, with primary voltage and frequency voltage held constant as percentage of terminal voltage. Okay. Or in the simple language, you can say that first of all, there is no load. So when there is no load, then E2 will appear across the secondary terminals of the transformer. And as and when the load is increased or it is increased to full load, so to assess what is the percentage of the difference of the voltage which is occurring due to the application of load at any specified PF. So it is the voltage regulation. Okay, so it is generally expressed in percentage. So it is percentage voltage regulation E2 minus V2 upon E2 into 100. Okay. So what is this E2 minus V2? As we have explained earlier also, for example, this is any transformer core and this is our secondary terminals where this E2 is EMF. So if there is any drop, resistive drop or reactive drop, then the voltage across the load terminals will decrease. Okay. So this is E2 minus V2 is nothing but the drop in transformer voltage at full load. Okay. So what is the drop? As you know that in the secondary terminals, now we are concerned with the secondary terminals only. So I am drawing only that part. So in the secondary voltage, the current flowing is I2. Say there is some resistive part and there is some reactive part, and then this V2 is there. Here it is E2. Okay. So this is the full load, you can say, when full load is connected. Okay, so I2 is the full load. So when this I2 is moving in the secondary terminals, and this is our R and X. Okay. So the drop, and due to this connection of load, as I have just told you that let us suppose that the load connected is inductive load. So when the load connected is inductive, it means that the current is lagging. Okay. Say this is the current, this is the voltage. So it is lagging by say any angle phi. Okay. So the power factor will become cos phi. So this drop in voltage, in simpler terms, we know it is I2R and you can say I2X. Okay. But if we calculate using vector algebra, it becomes I2 RO2. RO2 is the resultant voltage in the secondary side. I2 XO2 sine phi. Some of the values are neglected here. Okay. So this is this. So it is the output when we have assumed that the load is inductive load. So when the load is inductive, current is lagging. Okay. Or you can draw in a better manner. Say current is represented in the x-axis and voltage is represented in the xy plane. Okay. So if this is phi angle, we have used this. But if the capacitance, if the load is capacitive load, then there will be leading power factor. Okay. So when there is leading power factor, this phi becomes minus phi. Okay. Generally, current is lagging, but in the inductive load, but now it will become leading. Okay. So in the cos angle, there is no difference, but when the phi angle changes from, now what happens? Voltage, current is increasing, current is leading. So now the voltage becomes like this. So now if the angle is same, magnitude of the angle is same, then the polarity becomes minus phi. So sine of minus theta is minus sine theta. Therefore, when we substitute this angle phi by minus phi, this minus sign comes into the picture. Okay. So in general, we can say that percentage voltage regulation is represented by this formula plus minus phi plus minus I2 XO2 sine phi based on the load which is connected. Okay. So suppose that the voltage is transferred to the secondary side. Okay. In general, we know formula is V2 upon V1 is equal to K from the transformation ratio, and also this is equal to I1 upon I2. Okay. So you can say that the voltage when it is moved from primary side to secondary side, or voltage drop is considered from primary side to secondary side, it is multiplied by the factor K. Okay. This is voltage V2 and primary side V1. So it becomes KV1. Okay. So we can say that at the initial point of the KV1, we can say that this is the KV1. So this is E2. Suppose that the current which is flowing in the primary side is I1, and in the resistive components are this R1 and X1. Okay. So the drop in the primary side is I1 R1 and I1 X1. So the voltage or the drop component, when it moves from primary side to secondary side, it gets multiplied by the factor K. It becomes K I1 R1 and K I1 X1. Okay. Now this formula I1 upon I2 is equal to K. So we will substitute this I1 is equal to K I2. So it becomes K square I1, K square I2 R1 and K square I2 X1. In the secondary side, the current I2 is already flowing, and R2 and X2 are the resistive and the reactive components. So the drop due to the I2 is I2 R2 and I2 X2. Okay. So since in the secondary side only one current is flowing, which is I2, and we have resolved the resistive components of the resistive and the reactive components of the primary side to the secondary side. Okay. So the drop total drop has two components. One the resistive components, one is the reactive component. So the resistive component is these two and reactive components is these two. So we will add them as this, and it becomes I2 K square R1 plus R2. So it becomes I2 RO2. Okay. So this RO2 is the resultant resistance. Similarly, the reactive drop becomes I2 XO2. Next, we have to draw the phasor diagram. Now let us assume that it is assuming the inductive load. So when we are talking of the inductive load, suppose this is our V2 voltage. So we can draw the current I2, which is lagging. Okay. Now the resistive component or the drop due to the resistance is in phase with the current. So if this is I2 and this is V2, V2 is the voltage which load and is receiving. Okay. It is just the application of KVL. This is our input, this is our drop, this is our output. Okay. So input is equal to output plus drop. Okay. So this is our V2. Now the drops are explained in a vector algebra format. Okay. So this is our I2 RO2, which is in parallel with this I2. And this is resistive drop. Now we have to draw the reactive drop XO2, which will be in 90 degrees. So this is, now we will be joining this resultant. So this is the KV1. Okay, this is the input which we have given. These two are the drops, and we have joined these vectors to get the resultant. Okay. So now what we have to do, we have to take the magnitude. So this KV1 is equal to, we have to take the drops along the x-axis and along the y-axis, apply the Pythagoras theorem, and then we will get the result which we have obtained there. Okay. So what result we have obtained there? We have obtained there this result. KV1 is equal to V2 plus this. So this KV1 becomes E2. So it becomes V2, E2 minus V2 to get the same result. Okay. And if the load is capacitive, this phi will be negative. Okay. So this is the derivation of that.